So what we're going to do is we want to calculate the inductance of a solenoid. So we're going to use this actual solenoid. And I wrote down some of the number of turns, bit of an estimate. I didn't count every loop, kind of counted and then, to get the turns density. But yeah, I measured the length and the radius. So that'd be the cross-section radius, about 0.4 centimeters. And yeah, basically the inductance is just going to be the flux over the current. Now, it doesn't matter what current is. The inductance is a property of the solenoid itself. So even if there's no current, this still has inductance. So we can put whatever current we want in here and then calculate the flux. See, it might look like it depends on the current because we have an I here, but the flux is going to depend on the magnetic field, which also depends on I. And so those two are going to cancel out. Like if we put a 1 amp current in here, then we divide by an amp. If we put 2 amp current, we'll have twice as much flux. So again, we'll get the same answer either way. So we're just going to put some current in this solenoid. And then we need to find the flux through the solenoid. And then divide by that current. So to start out with, the magnetic field, mu naught Ni over L. Let's just say we put a current of 1 amp, because we can put whatever we want in here. So just to make life easier, let's say we put a current of 1 amp in this solenoid, and let's calculate the magnetic field. So we have mu naught So that's times 10 to the negative 6, so we'll put that on the bottom. N is 220. They're divided by 6.5 centimeters. Let's get rid of centimeters. And then the current we said is 1 amp, just to make things easier. So let's check the units. The amps cancel, centimeters cancel. We'll get our magnetic field in Teslas. So we're getting a fairly small value here. 1.26 times, I'm going to do this, 2.2. You know what, 22. Okay, so Tesla. So just to explain, we got 1.26 here. I'm just going to write 22 because that'll give us scientific notation. So we have a 10 left over and then a 10 here. And a 10 to the 6 on the bottom. So here, let's do this. Let's convert to milliteslas. So again, going over this, 1.26 times 22, so we took 10 out of here, so we have 22 times 10. I think we can get rid of this one. Okay, so we have 10 times 100 is 1,000, times 1,000 is 10 to the 6. That cancels that off. So this is what we have. So I'm just going to cheat and use a calculator. So I'm getting around 4.26 milliteslas. So again, with just 1 amp, we're not going to get a very strong magnetic field. That's something like you'd get from like a refrigerator magnet or something, maybe a little bigger, but yeah, not too much. Okay, now the flux would be the magnetic field times the area. Now this is a bit of an approximation, just like the magnetic field itself is. or this magnetic field applies if we have a very long solenoid. And again, this is fairly long, but when you get to the edges, they're going to spread out a bit. But again, just whenever I say like the flux is the field times the area, that's usually every time we calculate it, that's usually how it turns out. But we do want to be very careful that we're not making any assumptions that aren't justified. So first, we're assuming that the flux is the same for all these coils, which to a good approximation it is. Again, we'll get some spreading out near the edges, so this will be a bit of an overestimate. And we're also assuming that the magnetic field is parallel to the axis, because all these loops are perpendicular to the axis. So we assume the magnetic field goes right down the middle, and so that cosine theta term, I didn't write down what the flux is, but it has that theta, which is the angle between the normal vector and the magnetic field. So we completely ignored that cosine theta term. And again, that's true to a very good approximation. But, it's always, if you're going to make approximations, you want to be aware of them. So let's find the flux. So we have I'm going to convert back to Teslas. So we divide by 1,000. And then we have pi. Now the radius is 0.4 centimeters. Okay, so to convert to meters, we divide by 100. So we can say 0.4 is 4 over 10, and then dividing by 100, that'll give us 10 to the third. And remember, we need to square this conversion factor as well. So we're going to get a very small flux here. So the flux, let's get the number here. We have 4.26 times pi times 16. Now let's write it like this. And then times 10 to the minus 9th power. And that would be in Tesla meters squared. So again, this solenoid, fairly long but very small radius. So we're not going to get much flux that way. The bigger the area, the more flux you would get. But and again, a Tesla is a huge unit, so it's not terribly surprising that this is kind of small. So what we're getting is 214 times 10 to the minus 9, or 2.14 times 10 to the minus 7 Tesla meters squared. So that would be the flux through this entire solenoid. And then to find the inductance, we'd have the flux over the current, which was just 1 amp. So numerically, we're going to get 2.14 times 10. You know what I'm going to do? I'm going to do this. Let's say 0. Let's get rid of the 4. 0.21. That'd be times 10 to the minus 6. Tesla meters squared per amp. And now let's throw this conversion factor on here. A Henry times an amp is a Tesla times a meter squared. And so we will get our inductance in henries. And because of this exponent here, so the inductance, let's say 0.21 microhenries. So that would be the inductance of a solenoid like this. So again, remember, a solenoid is kind of designed to give you a lot of inductance. And this one, not so much because of the small area. But, yeah, so we're in the microhenry range. So if you're ever dealing with a circuit like in a lab, which, well, we did those online, the simulated labs, we can completely disregard things like inductance, because even if we're trying to get it, we're only getting microhenries. Now, yeah, this does not seem to have too much of an effect on our circuit. However, look at an example where we have a circuit with a battery and a switch, and we just turn it on. And again, this will prevent the current from reaching its maximum value instantaneously. I should point out that this can actually have a very significant effect on a circuit, because where these are really used a lot are in, let's say, part of their main use is in circuits involving alternating currents. They can have a very significant effect on those because the currents are constantly changing, and this is constantly a factor. But again, if you want to deal with circuits, that's kind of like an entire subject by itself. Like electrical engineers take entire classes on just dealing with electrical circuits. And without calculus, there's not too much we can do. One application you could think of, though, for something like this, like a solenoid, you can actually use something like this as a switch for an electrical circuit, where if you run a current through here, imagine you have like a metal bar inside here attached to a spring, or like say outside, and you can, if you apply a current, normally a spring keeps the bar outside, but then if you apply a current, the magnetic field will like pull this bar inwards. And so if you turn off the current, the spring is going to push it outwards, and you can use that to like establish a connection. So like if there's no current, you can have a connection, you can make like an electric switch this way. So like with no current, say it's touched a metal here, you can have a current running through, but then you apply a current in this branch, and that's going to break the connection and affect this part of the circuit over here. So again, a lot of uses for these things. But yeah, as far as inductance goes, in a direct current, this is not going to have too much of an effect. You won't really be able to see the delay. Kind of want to build a solenoid where you could actually hook it up to a battery and slowly see the current rise, but you would need a pretty high inductance to make that actually work. So haven't done anything like that. But okay, so I think that'll be it for this one.